Hi all, welcome to the fourth part of the video lecture on combinational circuits. And so far we discussed what is combinational circuit and how it is different from sequential circuit. And some of one example we saw in the previous video, like how to come up with the combinational circuit, particularly for that code conversion, that BCD to XS3 code conversion we saw in part 3. So once you get an idea, so before coming to this part 4, please watch that part 1, 2, 3 so that you will have an overview of it. Now we are moving on to some other standard circuit design that involves combination circuits, right? So on popular circuit is the adder circuit, inside the CPU, the arithmetic and logical unit ALU is going to add numbers for you, right? So when you're asking this system to add two number, it is doing that for you. So how this addition is happening on the background, right? Some digital circuits are involved, and how such a circuit is to be designed. So that is a question. So first we will see something called just addition of 2 bits, right? So we can extend that to addition of any number of bits, right? So everything is in the form of zeros and ones when it comes to computer memory, right? So when it comes to computer, for example, if you want to add two numbers, say suppose you want to add this 3, 1 second. Suppose you want to add two numbers, say 3 plus 4. So high level language you will be writing some sentence like that, but on how this is implemented on the background, you know that this 3 will be represented in some memory. Maybe it is an identifier or a constant, whatever it is. So there will be some binary representation for this 3 and this 4, right? So it can use 4 bit or 6 bit or 8 bit or 16 bit, depending on the type of the processor and other parameters. Those things are architecture dependent, but anyway, suppose minimum some 4 bits suppose I am using, then I can do this addition, right? So 1 plus 0 is 1, then 1 1, and this addition procedure, now I am telling you how it can be implemented using our logic gates and also that is what we are going to see. So first we will see the concept of addition of just 2 bits, right? Now sometimes instead of this 4 plus 5, and sometimes you have to add this say 3 plus 5 instead. So what will happen on the background? So 3 is like and 1 is this, right? So 1 plus 1 0 and carry is coming, right? So 1 plus 1 0 again carry, 1 plus 1 0 again some carry. So this carry may be discarded or something. So it is a normal addition, it is also part of the result, right? So what we are getting is like this is 3 and this is 5, you are getting 1 0 0, that is nothing but the representation of 8, right? So complete thing will be your answer. So whether you are representing using 4 bit or 3 bit depends on that. Okay, so anyways, hope you have this idea, right? So how this binary addition is happening. And now we are going to see just the addition of 2 bits, right? How this 1 plus 1 and 1 can be added, how this 1 and 0 can be added, 0 and 1 can be added, like that. We are not considering about the carry cases. In actual additions the carry will also come, so that the addition is actually 3 bits, right? So when you try to add 2 bits, on carry is also coming, so that you are trying to add 3 bits now. So that we will see next, in the next topic, that is full adder. So right now it is half adder. Half adder is particularly for adding only 2 bits, just 2 bits. So it is not considering this carry at all, right? So at least for the least significant bits you can use half adder for sure, right? So for adding the least significant bit, definitely carry is not going to come, so you can definitely use half adder. But from the second bit onwards carry will be coming, so you have to use something different. So this half adder is not enough. But anyways, we are just seeing as a starting point how this half adder is working. See, what is this task? So I have a half adder circuit. Let me denote it something like this. So this is my half adder circuit. So what is the input? So input and output has to be clear, right? So for any combination circuit design, so you have to be clear about the input and output. So I assume that just 2 bits this half adder is going to add. Let the bits be x and y. So here also when I am adding, let this 1 I am denoting by x and this 0 I am denoting by y. This single bit only, not the entire number. Okay. So when it is adding 2 bits, right, what is happening? There will be a sum, right? There is a sum and there is a carry output. So what is this S? This S is the sum output and this is the carry output. So when you add two bits, you will get a sum bit and a carry bit, right? So that depends. So when you are adding 1 and 1, 0 is the sum bit, right? So this is your so similarly, when you are adding this 1 and 0, this 1 is the sum bit. And what about the carry which is coming here, right? So the carry bit, right? So in this case, the carry is 0. So because no carry is generated. So like that, some carry will be generated and some will be generated. So that's all. So just let's observe that input combination. So this is the truth table, right? So x and y possibilities are like both inputs can be 0 0, right? 0 1 1 0 1 1. So two inputs are there. So 2 power 2 4 possibilities are, right? So when suppose you are giving something like x is equal to 1 and y is equal to 1, say, so that the sum bit, 1 plus 1, the sum bit will be 0. Sum bit will be 0. And what about the carry bit? There is a carry 1, right? So something like that. So depending on the type of input you are feeding, it will react, right? So when it is 0 0, the sum is 0, carry is 0. 0 1, the sum is 1 and there is no carry, right? 1 0, sum bit is 1, carry is 0. But 1 1, sum bit is 0 and carry is 1. So this basic addition concept is clear, because in the first module you are seeing that, right? It's the addition, all the in all means in hexadecimal addition, BCD addition, binary addition, everything you saw already. So the binary addition, now it is clear. So we are just looking at the circuit part only, circuit design, right? So that about it. For that we are seeing the truth table like this. Now what I need is, I have to express this sum and carry. These are all my output, right? So first output is the sum output. I have to express it as a function of the input x and y. That is my task. Then I have to express the carry output also as a function of the inputs x and y. So this is what is happening, right? So for any combination circuit, when there are n inputs and m outputs, each of the output you will be expressing as a function of all the inputs, right? So that is my task. So what is this carry? So this is my carry, right? And by looking at the truth table, you can see that this carry alone, when you see, this is going to give you a 1 only in one case. So this is a case where this carry bit is showing a 1, right? So you don't have to worry much. You don't have to depend on k map something. So you can directly write the expression for it. So what is that case? The carry is behaving just like the AND operation. You can see that. So this is just like the AND operation, right? So when the both inputs are 1, it is going to give you 1. In all other cases, it is going to give you 0. So the SOP expression for this is the min term. Only this min term 0, 1, 2, 3. Only min term 3 is involved. That is x, y. So this is the expression for carry. Is it clear? Right? So many examples we saw similar, right? So there is nothing that can create you any confusion. Now what about the sum? So when you are looking at the sum, look at the sum column alone. So where this sum is giving me a 1. So there are two cases. So we are trying to write the SOP expressions, right? So here the sum is 1 and here also the sum bit is 1. Right, two cases are there. So when I am writing this SOP expression, what I will be getting, the sum bit is equal to the summation of, this is my min term 0, min term 1, min term 2, min term 3. So I am getting it like a sum, min term 1 is active and min term 2 is also active. All others are 0. So this is nothing but sigma of 1 comma 2, right? Or what is min term 1? Min term 1 is x bar, because x is equal to 0, right? Min term 1 is x bar y. Similarly, min term 2 is x y bar. Fine, x y bar. So both of them are active, x bar y and x y bar. And this is nothing but, this is the expression of XOR gate, right? X XOR y. This is XOR gate. Hope you remember, x bar y plus x y bar. So that is the expression, right? XOR. So this is going to give you a 1 when both inputs are different. When both inputs are same, it is going to give you 0. So that is how the XOR gate is behaving. So you can either express it like this. This is this SOP expression, or you can express it as by a single gate, that is XOR gate. Accordingly, we have the realization. See, what is my sum bit? So the sum is given by the circuit. So x, you apply x dash and y in one AND gate. So this is going to give you, so the output of this AND gate is what, x dash dot y, and here I am getting x dot y dash. So both of them you have to OR finally, right? So that is your sum bit. So the sum bit is x dot y bar or x, what is it, yeah, x bar y, say see x XOR, right? So you can either express it using AND or realization, or you can simply use an XOR gate. So XOR gate, this is your XOR gate, right? So here you depend on uh, an AND gate and OR gate, right? So two AND gates you used and one OR gate used. So here you are using just a single gate, so that is going to give you the x XOR y as output, and both are same. So you can either use this circuit or this circuit, both are fine, right? So depending on the availability of the particular gate chips you are having, you can implement. Now what about the carry? Carry, I just need an AND gate, right? So that I can't use some other gates. So carry is just AND operation of x and y. So this is going to give me xy. So here also the carry is nothing but the AND gate is going to give you the carry. So that is nothing but x dot y fine. So this is a very simple concept, half order. They can ask you the truth table, the expression for sum and carry, the realization, the circuit, right? Everything is clear. And this is just like the block diagram, or the this is an overall circuit, right? So this is what is happening inside the circuit. So that's a detailed design, right? Similarly, the next one, definitely it is full adder, right? So now we need the generalized adder, where you should be able to consider the bits as well as the carry that is coming from the previous bit addition, right? So it is something like this. When I add two bits, ith bit of the number A and ith bit of the number B. So two numbers I am having A. So let me take this is my first number, some n bit number, right? Etc. A0. So 0, 1, 2, 3, some n minus 1. So like the total n bits are there. So B is another number containing n bits, right? Etc. B0. Right. So 2 n bits number I am having. So at any time I have to add 2 bits, right? So the bits I am representing by something like AI and BI. So let me write more clearly. So what I was doing, I have a two number A and B, and I'm trying to add them together. So what is my A? A is actually something like some n bit number, a n minus 1, a n, etc. because I started from 0, that is why up to n minus 1, so totally n bits are there. Similarly, b is b n minus 1, b n, etc. b0. So these two numbers I am adding, right? So this is actually general addition, and I'm getting a result that is Sn minus 1, Sn, etc. some S0. So this many bits I am getting. Now I am interested on the what is happening for a particular bit in between, some AI. I don't know what is this, some BI. So this can be anything, and I am getting a result that is SI, right? Now what will happen is this AI is followed by some bit like AI minus 1, because I am numbering like 0, 1, 2, 3, right? From right to left the number is increasing. So some AI minus 1, BI minus 1, and some SI minus 1 you are getting. So from that position, from this position you will get a carry. So that will be your CI minus 1. Why it is ei minus 1? Because it is generated in the I minus 1th position, right? So here this will be ai minus 1. I am not having space there. I hope it is clear, right? So this keep increasing, this 0, 1, 2, 3, etc. ai minus 1, then ai plus 1, like that it is going. Similarly, here also bi minus 1, bi plus 1, etc. si minus 1, si plus 1, etc. And when you are adding the position ai minus 1 and bi minus 1, you will get a sum si minus 1, and you will get a carry, that is ei minus 1, and that you have to consider for the addition here. So this is a general scenario. So you are trying to add some ith bit of the first number and ith bit of the second number, and the carry which is being generated in the position following it. So something like a ci minus 1. These three things you have to add. So so this is a general scenario, but here these inputs I am representing by x, y, z. So x and y are actual bits I have to add, and z is the carry that generated from the previous addition. So right now I am in the ith addition. So the carry generated from the previous addition I denoted by ci minus 1. I minus 1 the level. So all of them I am trying to add, right? So I need a circuit for that. So how my circuit will be looking like? So this is again a combination circuit, and I am calling it as a full ladder circuit, right? Because why it is, the previous one is half order because it is not considering any carry. Here it is considering carry also. That is where the addition is complete, right? Full. So that is why I can call it as a full adder. So for the full adder circuit, now I have 3 inputs. What are they? X, Y are the 2 bits I have to add and z is the carry from the previous position, right? So, or ai, bi, ci minus 1, in any ways, just variables only. You can give it a meaningful name like ai, bi, ci minus 1, fine, right? And I am getting a carry. So this is the ith carry, this is the previous carry, okay, and I'm getting a sum bit si. So here in the textbook they are denoting it by the sum bit and a carry bit. So this is my task. Now I have to, as usual, I have to find out what, so these are all the inputs. So now I have the circuit is containing 3 inputs, right? So using 3 input, 2 power 3 input instances are possible, input combinations are possible, and those instances are listed here. So some 0 to 7, 8 combination, right? Clear, x, y, z, that can vary from 0 to 7. Now what about the sum bit? The sum bit you have to express as a function of all the inputs x, y, z. Similarly, you have to find out the what is carry bit as a function of x, y, z. So that is your task. Once you get it, you can implement it. So that will perform this task for you. So what is your requirement? So this is a design requirement that you are representing by a truth table, right? Now each of the output variable you are going to express as a function of all the input variable, and that you realize using the circuit, and that will do this task for you. So that is the idea, right? Hope it is clear. Many examples we will see, we already seen also, right? So now let's see how this addition process is happening. The truth table completely, let's analyze 3 bits, and the addition, normal addition, so accordingly you fill the table. When all bits are 0, the sum is 0, carry is 0. So here on 1 is coming, on 1, single 1. So that sum is 1, there is no carry. Here also single 1, sum is 1 and there is no carry. Here there are 2 ones, right? So 1 plus 1, I am getting a sum 0. Is it clear? So I am looking at this row. 1 plus 1, I am getting a sum 0 and I am getting a carry 1. Okay, so this concept is clear already, right? So here I am, there is a single one, so I am getting a sum 1 and a carry 0, fine. Here 2 ones are there, sum is 0 and carry is 1. Here also 2 ones are there, sum is 0 and carry is 1. Now when 3 ones are coming, 1 plus 1 plus 1, what is that? It is 1 1, right? So that means sum is 1 and carry is 1. Right. So this addition process, I assume that you already know because it's a very simple concept. Right, and the addition, when you studied it, it's already there in your mind. Or simply 3 ones, 3 in binary is 1 1, right? That's all. And 1 is coming and 1 is the carry. So it's a simple concept, right? So that's all. So once you have this table, so now you understood how to fill the table, right? So sum bit and carry bit, like that you write. Now you find out what is your carry. So see, you can see that the carry bit is going to give you a 1 in positions like this is min-term 0, min-term 1, min-term 2. Min-term 3, min-term 4, min-term 5, min-term 6 and min-term 7. So now let's see. So the carry bit is going to give you a 1 in here it is going to give you a 1, that is min-term 3. Now you are getting a 1, m5, m6 and m7. So let's see that. So the carry bit is actually, so this is your carry. So this is the minimal expression for it. So before that, let's see this, what is this carry? So carry bit is sigma summation of the min-term 3, min-term 5, min-term 6 and min-term 7. Now we have the the truth table, right? So in using the truth table, totally 8 combinations. So 8 cell truth table I am having. So x, y, z, like that I am writing this, labeling everything you know, right? The gray code labeling everything you know. Now if you are looking m0, m1, like that, so which are all the minterms which are active here? M3 is there, right? So this m3 is 1, then m5 is active, so this is m5, right? M5, then m6 and m7, right? So accordingly I fill the k-map for it. I am removing those things. So the k-map is clear, right? Now you can have the grouping. So how can you group? The ones you can group like this is one grouping. So tell me what is the corresponding term for this. This is this x is vanishing, then y and z, right? So this corresponds to y, z, fine. And similarly, what is the next grouping? The next grouping is see this one, and now tell me what is this? This corresponds to x, and y vanishes and z, right? X z. So this corresponds to x z, fine. Now what is the last one? That is these two ones, right? These two ones. So when you are grouping like this, x is there, y is there, and z vanishes. This corresponds to xy, fine. So accordingly I am getting this expression for the carry. So you can see that all three variables are coming like x, y, x, z, y, z. Now you can remember it also, because this will help you in some future circuit design. Okay, so it's better to remember this if possible. Otherwise, you write the circuit and derive it. So all three variables in all the three combinations, x, y, x, z, and y, z. So that is the carry. Now what about the sum? So when you're looking at the sum bit, you can see this. Yeah, let's observe the table. What's going on? So the sum bit is going to give you a 1. See, this is your sum bit. This is a case, right? So m1 is 1, m2 is 1, and what is this? This is m4 is 1, and finally this m7 is also 1. So I can write it like a, so this is equal to summation of m1, m2, then m4, m7, right? So this many fields are active. So you can see that when I'm filling it in the table, m1, m2, m4, and m7, right? So these things are, so I filled the tables. Now see how many groupings are possible. So now I have a difficulty, because I can't group more than one rest just like this, because all ones are like this one. When I'm joining, it's not possible for me to combine it with any other one, because it's not following the rules of K-map, right? So everything is looking independent. So that is a difficulty I'm having. Yes, so that about it. So this is something looking. So what is this term? X, y bar, z bar, right? These things are like y bar, z bar. So where it is x, y bar, z bar. So this is this one, right? Now let's take another color. So what is this term? This is x bar, y bar, z. X bar, y bar, z. Yeah, this one. Now where is this one? This is x, y, z. So this is this term. Fine. Now finally, yeah, what is this term? This is like x bar, y, z bar. X bar, y, z bar. See, like that I'm getting all the terms, right? So this is how I'm getting the sum. Now that's all. So this is the standard SOP realization. It's not canonical SOP, it's minimal SOP, right? So minimal SOP. Here actually canonical SOP, for some canonical SOP, minimal SOP, both are same, because that grouping is not possible for me. So like that the ones are distributed. But you know, you can make it something different, some very simplified expression you can see. Let me give you a hint. Maybe we will see in the next video, but before that you can try by yourself. Can you minimize this expression in a different way? Because this K-map is not going to help you. This is the only way you can minimize. But can you use the normal Boolean algebraic rules and all, or can try using, maybe let me give you a hint, XOR gate, and try to come up with a very small expression, say with the help of XOR gate. So that is the task for you. You can try it, right? Fine. So right now we are not worrying about the other gates and rules. So we just need the realization using AND OR gate, right? So the minimum SOP I am getting, and it is a canonical SOP also in case of sum. But in case of carry, the minimum SOP is different. Canonical SOP is this one. There is a summation of M3, M5, M6, M7. But here it is different. It's a very small term expression I am getting. So now you can implement it, right? So you just use a circuit like here for implementing the sum. You have to use 1, 2, 3, 4 AND gates, right? 3 input AND gates and a OR gate. So you can use like this. This is AND gate 1, AND gate 2, AND gate 4, sorry 3, and gate 4. So 4 AND gates you are using, and finally all the outputs you are ORing, and you will get the final sum. Right. Now what about the carry output? Just 2 input AND gates are enough. 3 2 input AND gates are needed, and sum 3 input. So here you can see that here you used a 4 input OR gate, but here it's enough to have a 3 input OR gate. But basically we have 2 input OR gate, but using them repeatedly using them, you can realize it, or directly some 3 input OR gate chips are also available. Similarly here it is a 2 input AND gate, but here I am having 3 input AND gates. Fine. So anyway, this is clear, right? So this is a realization of sum and carry. So that about the half adder and full adder is a very important topic. Now we will see some variation of it. So that is something I already assigned you, like try to derive a different expression for the sum and carry. So that try to see whether this full adder can be implemented using half adder. So that is the way you have to think, because in half adder basically we have a sum as the XOR of x and y. So can you express the sum of full adder also using the XOR function? So that is the first thing you have to look at. And if that is the case, can you implement a full adder using a half adder? So that is the task you are having. Similarly, carry also can you adjust accordingly, right? So you can try it yourself. We will see the solution in the next video. Yes, thanks for watching.